Morning, everyone. You stragglers might come in a little later, but that's fine. They'll miss the good parts. Anyway, my name's Bill Mercer. I'm with PMAC. I have the privilege of serving on the board there. And I also have the privilege of introducing our speaker this morning, Floyd Baker, Vice President for Atria Canada, Inc. And Floyd's got both 39, 40 years of experience.
42, actually, yeah.
42, but yeah, who's
But who's counting? Yeah.
Yeah. Better that he looks must have started when you were 10.
No, I'm old as dirt.
Anyway, to provide valuable insight, perspective, digital assets and IIoT. He's an asset integrity digital strategy advisor with global communities. Supported a lot of industry and throughout his career has worked to explain complex digitization strategies and all those digital wonderful things to dumb guys like me who are in the industry and have 40 plus years of experience on the other side of the world. So we'll I'll keep my introductions short and brief and introduce our esteemed speaker, and we can enjoy his topic.
Thank you, Bill. Appreciate it. Appreciate it. So enough for the boring stuff. Actually, we're going to start with some boring stuff. We all know about Integrity Operating Windows API 584. We're going to talk a little bit about initially a little about where it started, how we kind of apply it to our businesses, and of course, kind of a little bit of history and evolution and some of the learnings or experiences we found going through that evolution. And then, of course, we're going to introduce a new era of IOWs and how you can manage them in a more automated, IoT-driven way. So from an introduction standpoint, we know what integrity operating windows are designed for. They're designed to where one can manage or actually first identify and document your upper and lower boundaries of safe operating conditions for a specific asset in a facility. Typically, that's metallurgically driven. Also, what this does is provide really good insights and information on how to manage those assets and mitigate that kind of risk of damage mechanisms and accelerated damage rates. Some of the key process variables are what we kind of identify the process variables for which the asset was actually designed to operate in, and then at what point upper and lower boundary does it breach and get into an unsafe situation for the asset in and of itself. What we're trying to do here is of course identify opportunities or possibilities where corrosion, fatigue, stress corrosion, any kind of cracking or any kind of a damage mechanism might occur on an asset when you're operating outside those design parameters. What do IOWs do for us? They actually create an opportunity for us to enhance and make our inspection activities a lot more accurate, understanding what kind of damage mechanisms might have affected that asset and what kind of technology we use to detect that kind of damage. It also helps in providing maintenance strategies and understanding what repairs might be required as a result of those kinds of activities. So you can pre-plan for those and not have to identify them during a shutdown and everything happens at premium rates. It also helps prevent catastrophic release. We'll talk a little bit more about the three different categories of IOWs in a moment to expand on that topic. It's designed, of course, to reduce downtime because you understand when you have these upset conditions and how that might negatively influence your shutdown schedules, if it's a turnaround shutdown, squat, crash, whatever the case may be. Also designed to extend the life cycle of the asset because once we understand those upper and lower boundaries, we know to operate within those lower boundaries, thereby extending the life, minimizing the damage associated to that asset over its life cycle. So they can be used in any environment. That's one thing one point I wanted to make. API primarily focuses on refineries, but also petrochemicals somewhat. But this concept alone can be used in any asset-intensive industry. It doesn't matter if it's a power plant, pharmaceuticals, if it's agricultural, pulp and paper. The same concepts can be used because everybody's going to still build their assets to ASME, construct their assets to ASME. They're still going to maintain and monitor and maintain them to API. And all the same issues are apply. Metallurgy against the process, right? So the concept can be used across any vertical in the industry. So those three different categories. There's of course critical, which is an inherent acute type danger. If the operators start to see their boundaries breached, upper or lower, this is a situation where you'd have to do something quickly. Could be hours, could be a day, but mostly hours. Standard is a little less acute and something that could be monitored over time while one figures out how to fix the problem. We'll talk a little bit more in a little while about how you can actually approach those in a lot more expeditious manner as well. And then of course there's informational IOWs, which would be a more chronic type failure. You know you're operating outside that parameter, you know you're doing some damage, but it's a slower growing damage mechanism. So you have some time to plan for whatever you may have to do to either mitigate or repair the situation. So the history of IOWs. Actually, we were using IOWs many, many years ago before it was even called IOWs, but it was on critical assets. Like one time I can recall on a loop reactor, but it operates at 40,000 PSI ethylene. So you can imagine that's pretty critical asset. So we had created these boundaries and even trained the operators on where those were and who to call if they breached them. But that's pretty old school now. You know, we have ways of doing that now, more automated. But in 2014, the first publication of IOWs of API 584 was published. Of course, we had a lot to learn. So over some years, we realized that the corrosion control document actually should have came first, understanding the corrosion first, and then applying those upper and lower boundaries based on what the design process was supposed to be. So the second edition of API 584 came out in 2020, and it addressed a lot of those issues and related more to the CCDs. And of course now, and we'll talk more about it in a moment, we have IIoT to help support all this in a more automated fashion. So the traditional applications focused on the typical time-based API 510, 570, and 653, and of course provide critical inputs to inspection plans. Basically, that's what it's designed for, to help better understand how to plan your inspections on known or possible defects that might have occurred during these breaches. They offered the inspection engineering departments to be a lot more proactive in terms of how they plan their inspections and of course how they plan their maybe repairs or replacements. You could do that beforehand instead of during the outage, instead of having the findings during the outage and then having to scramble with overtime and spare parts and all that just to get them operable again and get your unit back up and running. It of course helped prioritize your inspections. Of course, using the time-based method, not the RBI, but the time-based method, you still understand there's a priority if you have assets that have known breaches. You'd know that those should move to the top of the list and they probably need to be looked at in that particular outage. Then the RBI came around, of course, and now that helps with a better RBI assessment because now you actually understand that the damage mechanism may have occurred, and this is a direct influence on your probability of failure component in that algorithm, right? It's going to make a big difference when now you not only think it's not only as it may occur because that it is in that environment, but it's that you saw that breach of the integrity operating window and you know it's been exposed to that higher damage rate. So you know better how to plan the inspection and of course what technology to use to detect, size, and characterize. And even you might even be able to do that pre-turnaround in some cases so that one can plan and of course make the repairs during the outage and it be pre-planned instead of post-planned. So now we're going to talk about IOWs in today's digital era. A little bit different now since the onset of industrial Internet of Things. You know, everything is internet accessible. You know, our smartphones give us access to all kinds of information all over the world. An entire platform, as a matter of fact, that can actually access this kind of information. You can access it through your smartphone or a tablet from anywhere. And that was the first steps of IoT, or it was IoT, Internet of Things, with our mobile phones, were the first smartphones. Nowadays, they can be used in industrial Internet of Things in these kinds of environments. One can not only manage all the inspection data, inspection activities, non-destructive testing activities, planning, scheduling, visualize, contextualize through 3D models, 2D schematics like PNIDs, PFDs, plot plans. All of this information became accessible right through your smartphone or tablet. So industrial Internet of Things is the enabler for the digital era of IOWs. A lot of other things very useful in terms of IoT. It brought us digital twins, actual virtual replicas of the actual physical object in the field or assets in the field, and being able to visualize real-time data. So you kind of bring that visualization to life with real-time data in a digital twin. You can use wearable technology to access information as well. Things like RealWear, Microsoft HoloLens, these kinds of things can be used to access it and do inspections or tests, all hands-free. Computer vision is very, very handy in this situation, especially when we're referring to digital twins. And of course, the remote sensors, the things that make it all possible, being able to capture sensor data in that digital twin, utilize that sensor data in your ROWs, and then influence your RBI, and then assess your IDMS, your inspection data management system. So we look at the world in industrial Internet of Things in two spaces. One is IT, which is information technology. We've been familiar with that for a lot of years. This is all your legacy systems like SAP, Maximo, Canary, Upkeep, many other different kinds of EAMs, ERPs, CMMSs. So an integration to those is very key because the work happens in those. The actual work orders, notifications, work orders, materials, resources, all happens in your legacy system, in your EAM, ERP, or CMMS. However, the identification of the work and what work gets done and the criticality of that work happens in an IDMS, integrated to an RBI, integrated to an IOW. So that when you have issues, you can actually generate notifications and automate those if you like, if you wish. Automate those notifications to generate notifications and convert to work orders in your legacy systems. So that's the IT side of the world. That IDMS sits in the middle, that IDMS and IOW and RBI sits in the middle between, it's the bridge that bridges the gap between that and your operational technology, OT environment. The OT environment being your sensor data, if that's DCS, PLC, SCADA, even data historian, or even directly to remote sensors that are to the cloud or to a gateway, capturing all the sensor data. Now, after doing this for quite a while, it's really obvious that the most efficient way to do that is through data historian, because typically you capture all of your data in that historian. So if it's Pi or Canary or whatever it is, you're going to have just a buffet of sensor data to capture and bring to life in that digital twin. There's always cases in some processes where you might have temporarily mounted sensors. Maybe it's UT, phased array, thickness, or cracking. Maybe it's eddy current, but these are temporarily mounted systems. You can also connect to those too, but the most important part is to connect to them, is to integrate to them, capture that data so they can be used in that IOW and in your RBI algorithms. So integrations are very key, especially for the digital twinning aspect of it. Integrating also with non-destructive testing devices. Nowadays, they're starting to the manufacturers are finally creating devices that are Wi-Fi or Bluetooth enabled. So there's ways to integrate to that information. Saves you a whole lot of data processing anyway, a lot of manual handwriting, and then of course, manual data entry and all that. So if you do it at the edge, at the asset itself, then you've eliminated a whole lot of work. Also humans, we mentioned the cell phones a while ago. Now inspectors can go out and capture their data right there on their cell phone or a tablet. And the cool part about this is being able to structure what they capture instead of just a piece of paper and a tablet and writing down, inspectors can write a novel, let's just be honest. They can write a whole novel about an asset or component on the asset and make a report turn into 4 or 5 pages. And it's really good information, but it's really only good the moment that you read it. it's not going to provide any value in terms of analytics, right? So having that ability to write whatever they want to write is fine, but capturing data in tick boxes, drop-down menus, controlling and structuring the data that they capture so that one can use it on a more global scale in terms of data analytics and providing more value, more aggregate value to an entire unit or a plant, whether that be coatings conditions, insulation condition, better helps you plan for the future when you're talking about, I need to plan for a coatings upgrade in this unit because I see all the inspectors, all the reports say coating failures, right? To this extent, or same for insulation or whatever the case may be. So structured data, this is key too, but being able to connect this data that you capture directly to the platform, again, you kind of create a more efficient workflow. Work goes straight from the asset to the database. Of course, edits can be made, all that kind of good stuff, but the most important part is everything that you witness, pictures you take, video, audio, all of this data can go straight to the platform. And then it's just a matter of cleaning up the draft and saving it as the document. This is a visualization of what the ecosystem looks like. We're here talking mostly about IOWs, but there's a relationship to everything here. Your IDMS is really the bridge that jumps between the IT and the OT that we just talked about. It's integrated to your legacy systems or your ERP, EAM, or CMMS. We're using SAP as an example in this visualization. Your IDMS is capturing data from NDT devices, integrated to NDT devices, also from inspectors and technicians, directly to the IDMS, so you're integrated to your humans. Your RBI is integrated to your IDMS, so you're able to share inspection data for your RBI analyses. You're integrated to your IOW, so you're actually sharing information that operates outside of those conditions and creates a higher damage rate or could create a higher damage rate. And you're feeding that information straight to your IDMS, but also your RBI to influence that probability of failure component of the algorithm. Sensors are key here because this is a large data capture for you especially in terms of the IOW. IOW and the digital twin. Those two go hand in hand. Benefits are kind of obvious, but we'll talk about them anyway. Using this new generation of IOWs, you're really talking about instant notifications. That could be an alarm if you're getting close to a breach. That could mean a notification, an email saying you've breached. It could mean any kind of alarm or notification to let someone know that you're operating outside of your IOWs. Documenting this in a digital fashion, not only through a digital twin and being able to visualize not only how you've influenced that specific asset, but what about the asset upstream? What about the ones downstream? What about the whole system? Being able to visualize, contextualize all of this information through real-time data in that digital twin is huge. Being able to trend that data and overlay those different types of sensor data, if it's pressures, temperatures, flow rates, maybe pH, maybe CO2 levels, all this information stacked so that one can start to see how they influence each other to get right to the root cause of what happened in the first place, so that you not only mitigate the damage that could occur, or at least limit its exposure, but you can also mitigate the problem from ever happening again in the process with process conditions. So the benefits of IIoT with IOW, of course, as I just mentioned, you can trend all this data so that you have it for future reference. Even in the case that you fix all your problems go away, everybody goes back to bed and takes a nap or whatever. Bottom line is you fix the problem, but you can trend this data for future reference. This is where your root cause analysis comes into play. Like I talked about, you can actually look at this, look at the event on a grander scale, more holistic scale as it relates to the system or even the whole unit, and determine what caused it in the first place, drive to that root cause, and fix the root cause so that it doesn't happen again. So outside of the IOW, or actually around the IOW, we have the 510, 570, 653, your codes and standards, recommended practice, RBI 579. These are all influencing each other. You know, your time-based inspection or your inspection standards tell you how to go out and perform the inspections, and your IOW feeds you information to tell you what kind of inspections and what technology you need to perform the inspections. Using RBI methodologies, you of course can consider that probability of failure to make your risk assessment a lot more accurate because of known information and not just assumed information that you would normally use in your RBI analysis. 579, this is huge as well because you can better understand, instead of trying to determine what kind of damage this is, you know the conditions that were taking in place when the damage occurred. You can better understand what occurred and what kind of damage mechanism it is, and of course, what you do about repairing and or replacing that particular asset. So we'll touch a little bit more on the role of the digital twin. Of course, not a requirement in this whole situation, but a digital twin to me is really handy because of that ability to visually contextualize information. I read a article, it's been a few years ago, actually during the lockdown, and I think Google were the ones that published it. It was about humans and how they consume data. And there was a little meme in there that talked about humans have an attention span the size of a goldfish. And I thought, well, that's kind of rude. But if you think about it, it's true. We've had our mobile phones forever, and you flip and scroll through everything. And man, I can flip through LinkedIn and all, just flipping away and then just stop on what catches my eye. But then in a minute, it's gone. I'm on to the next one, moving on. So anyway, I just thought that was funny when I read it. Nowadays, it makes sense to me. So being able to look at this information, though, in a digital twin, all the different sensor data that you can look at, whether, again, we talked about flows, we talked about pressures, those two things influence each other. As far as damage mechanism, we can talk pH, CO2 levels, any kind of sensor data that you capture, but even your analyzer data. So you've got sample points where operators take samples, they send them off to be tested. They come back with results. Those results can still be put in. So you still have not as a high frequency, but you've got twice a shift that they're actually testing for the product quality, right? Different purpose for doing it. They're testing for product quality. So on spec, off spec, how much money am I getting per pound or per barrel or whatever for this particular product? But that data is still very useful in terms of your IOWs to understand how you've influenced an IOW with a specific molecule. So, and then there's also there's also a gauge out there that is not censored. Manual gauges, whether they're liquid levels, whether they're pressure gauges, dial gauges, whatever they are. Bottom line is those operators still use those gauges. You can capture data with those mobile apps that we talked about to where they're actually doing this on paper in the past, and they're writing it down every time, twice a shift in their rounds, and that goes in the logbook. Well, if they do it from a mobile standpoint, from a digital standpoint, then you can actually utilize that data here as sensor data. We call it humans as a sensor. So now you've added two data captures. You've added the operator themselves and the non-digitized gauging. You've added the sampling from your analyzers and from your sample stations from the product quality team. And you've done all this digitally using mobile apps. Being able to visualize that, there's also a lot more things it can tell you. Most people have 3D models of their plant from when they were constructed. Somebody's going to laugh, I'm sure. Okay, most people don't really, but it's easy to actually create a 3D model of a plant. If you don't have 3D models, there's actually technology out there that can create a 3D model in the platform, an inspection data management platform, using only dimensional data. So that means if you've got a U1 form for an asset, just those dimensions, you can create what we call kind of a Lego asset, much like this twin you see here. These are all just created from numerical data from a U1 form, or if it's pipe, it's the piping specification. The only limitation you would have is, of course, the length of the pipe, because your spec won't talk about that. So you either go out there and get that length or estimate it, or again, we're talking about a digital twin here. So point cloud is usually involved. You laser scan your facility, and your point cloud data is geospatially referenced and can be used for those measurements. So you can still create a whole 3D model of an entire system, an entire piping system using only dimensional data, the length coming from your point cloud, the rest of it coming from the platform. So having a 3D model adds value to that digital twin because it can still tell you other things. You can colorize that 3D model based on a lot of different things. It can be the process that's in the pipe. So you can see every single pipe, every single vessel that's influencing or engaged with any specific process in your facility. You can look at things like schedule state. Do I have inspections past due? And I can look at my whole plant and see I've got a lot over past due here, some over here, wherever, but you can see where you have past due equipment or piping in your facility. And when I say past due, that could even mean PMs on instrumentation. It could mean PMs on your fire suppression systems. It really doesn't matter. If it has a schedule, you can see it in this digital twin. In this case, we're showing the colorization. We have the laser, excuse me, the point cloud overlaid on that 3D model, but we're using the 3D model to show colors, to show the actual risk based on the color palette in your risk matrix. So now you not only understand that you have risk because you performed an assessment, but now you know where that risk is in your facility. Geospatial information to me is really valuable. So I'm not sure how early we are, but okay. Great. So we'll sum it up. Originally, I mean, in the early days, IOWs evolved in the industry. Originally as a concept, needed to understand and impact the operating condition of damage, operating situations and conditions that could be caused by damage mechanisms. And again, I remember when it wasn't even called an IOW, it's just something we did. I'll give an example. One of them was a reactor in a toluene disproportionation unit in Baytown, Texas. And it's a big giant reactor. And back then we didn't have IoT. That wasn't even a thing. It was nothing actually. But what we did have is contextualization through visualization, right? Humans consume data better visually than they do from tabulations, right? So this reactor was like 3.5-inch steel, about 10 or 11 inches of casted insulation inside, and then of course a stainless steel sheathing inside. And you've got TIs running all the way down through the different beds of the catalyst, of course, and of course PIs that are strategically placed as well, but those are still just very strategically placed. To get a picture to contextualize the whole situation, we actually painted the thing with a green thermal coating. So it's green, it's a pretty nice green. We called it a pickle because it was a vertical 80-foot tall and probably 24-foot in diameter. And you look out across the unit, it looked like a giant pickle out there. But that thermal coating, we could visualize hot spots, failures in the castable insulation and or sheathing, stainless steel sheathing, just because it would start turning white. And then of course, as that time went by, it would start turning brown or shades of brown and then into black. And of course, the further along you get, you might want to shut down and do something. But that was our visualization then. It was the actual asset, not the virtual asset. So in the new times, we actually get to use real-time information. However, it's in the virtual world to make these kinds of decisions long before they ever happen. So as I mentioned, it evolved as a corrosion mitigation requirement or need, better understanding. We design our assets to operate in the processes that they're supposed to operate in. However, there's always situations that they're outside of those, whether it be startup, shutdown, upset conditions. There's always situations where they're going to see something outside of what they were designed for. This is a way to better understand how those influence the life cycle of that asset. And are they really causing accelerated situations to shorten that life of that asset when in fact, if we're just looking at our IDMS, it says, well, our corrosion rate's mil per year, 2 mils per year. We know how long it's going to live. Well, do we really? Right? It's a way to challenge that. So we mentioned how it enhances the RBI. This information is really valuable for an RBI because it's a little closer to real time. It is real time actually to an RBI assessment, making your RBI assessment far more accurate than you could ever be just in a conference room locked up doing an RBI assessment with a corrosion engineer, process engineer, and inspector, and then mechanical engineer, and all these subject matter experts. You can actually have real-time data to make those decisions on. IoT changed the whole world. That made, as I've shown you here in this short presentation, this made the whole world able to look at this through a digital representation of an entire plant or unit or asset and make a more holistic decision, or make use a more holistic decision based on a more holistic view of what's actually going on. And it's all based on near real-time data. This leans straight toward better turnaround planning, shorter turnaround run lengths, and shorter turnaround timeframes. So overall, it's a huge cost savings. Anybody have any questions? Oh yeah, I forgot.
Thank you, Floyd. Great presentation on IOWs, right? And like you said, we get to IOWs starting with corrosion control documents. My voice is, corrosion control documents. And as part of developing corrosion control documents, we identify damage mechanisms, right? So then eventually get to IOWs, which are then measured using the technology, right? Has there been any mapping done? So damage mechanisms, they come out of APA 571, I guess, right?
Mm-hmm.
So, and the APA 571 lists about 65 or 66 or close to 70 different damage mechanisms. Has there any mapping been done? How many of those damage mechanisms, 60 plus damage mechanisms, can be monitored through technology today?
So to me, it's not just those, it's many, many more, because remember API, as we mentioned, is predominantly focused on refining and then a little bit of a lean toward petrochemical. There's so many other processes out there that are influenced by different damage mechanisms. So that list is much longer. But when you're talking about IOWs and how to map that data, really it's an algorithm. So it's not about how many there are, it's just about what are the details around it to create that algorithm. So if it's hydrogen-induced cracking, if there's something that, whatever that algorithm looks like, and if there's something else that looks like it in another industry, well, yeah, you can use that algorithm as the basis and just fine tune as you need. But creating a new damage rate for a new damage mechanism, it's just code. It's really nothing to software. It's easy. As long as you have an understanding of it, as long as you've had some research that props up, like NACE research that props up a genuine damage rate in certain conditions, whatever temperatures, whatever pressures, how those two influence each other, and a damage rate that occurs in that situation. So the numbers of damage mechanisms path, there shouldn't be there's no end.
My question, maybe the other way of asking the same question is, do we have sensors or technologies to measure all or most of those damage mechanisms that exist in APA 571 today?
To measure them.
Yeah, to monitor them, right? So
to monitor, yes.
Yeah.
Monitor is easy. Again, that's just a matter of catching the sensor data. If you have the right sensors in place, you
so
can
do we have the sensor technology?
That's the key. Okay.
Yeah.
If you have that sensor, if you have the sensor in case, I mentioned a couple of one that I see quite frequently are pH and CO2. If you have those sensors in place, then of course the data is captured, then it's just software and it's just code and it's easy.
Okay, thank you.
So it's all the situation that I've just defined is all based for IoT. It's based on IoT ability. That's the enabler. The contributor, the key contributor is going to be the sensor. Because if the sensor isn't there, IoT doesn't do me any good.
Anybody else have questions? We still have a few minutes. I actually do have one. I'm from the power business.
Mhm.
So a lot of our equipment, it's either very difficult or very expensive to put adequate sensors in order to capture that data. So say steam turbine subject to root cracking on the or the low pressure turbine blades.
Mhm.
Very difficult to monitor. That's always it's still going to force that outage just to look at it.
Yes, I agree with that. I mean, and it can. However, our access to, they could still be permanently mounted, but temporarily mounted sensors, people make all kinds of sensors now. It's just a matter of where do you put it to make it stay. And most are wireless. Some are wired to a gateway, and of course you can access through the gateway. But in that particular situation, it'd just be a matter of where could you place a sensor, because you can actually measure things like, when it comes to IOW, as I mentioned, they really are a concept that should be used across all industry sectors, but also disciplines within that sector. We're not talking about just 510, 570, 653 anymore. We're talking about pumps, rotating, compressors, reciprocating, turbines. It's just a matter of the right sensor and the place to mount that sensor to capture the kind of data. If it's vibration, axial vibration, something like that. There's ways you can actually create a benchmark, if you will, to know what good looks like, to create an IOW around that. And I've seen this happen many times in similar situations to yours.
I think one of the
Just say.
well is the loss of a material within a piece of equipment, such as a turbine blade, where you've got a corrosion mechanism that will cause a failure, blade liberation route, for example, and it's not detectable by any technology other than the human eye, pulling it apart, going through the expense of the physical inspection.
Yeah.
But I think what you mentioned earlier, one of the important things is being able to take that inspector's findings and transform that into a digital signal that can be used by your other systems downstream. Right.
So that's definitely the case. It is a matter of documenting their findings so that it's usable in the future. It's analytical. But the other part of that is, while that damage takes place, though, and you're losing material, you're actually changing the motion. So when I mention vibration, it's still very valuable, because as you listen to vibration over time, you're going to hear it progressively get worse, which also is data. That means that you're figuring out, when does it get so bad? How long can I push this envelope? So it might help you better understand how to extend the life cycle, if possible. And again, I don't know this for a fact. I'm just saying that it sounds like we know that if it's turning and it's losing mass, and are all blades losing the same mass at the same time, there's bound to be some kind of vibration. Can you measure that vibration to determine the actual over time? Because you wouldn't do it in one run, right? You're going to do it in a few runs and start having some data points to understand, when does my vibration change and how long does it change, and over time, how long does it change over time, I should say.
Not yet, but probably get there.
Yeah.
A 50 blades.
Yeah.
Turbine drove 10,000 RPM at vibration signal is very heavy.
Yeah, there's a lot of noise. A lot of noise.
I see the sensitivity growing and the algorithms that they're producing.
Yeah.
I'm not being loud enough. I'm being loud. No,
Recording.
Yeah, good. Yeah. So those kind of failure modes, those are the ones that we are, I think, advancing towards with the new sensors and the technology and the software that's being written behind them for detecting those kind of otherwise hidden failures.
Yeah.
So we see the vibration spikes, but by the time we see the vibration spikes,
Too late.
it's a startup and the blade's already gone. So,
Right. Right. Yeah. So filters, that's the key, filters.
Anybody else have anything? Because I have another one.
Okay.
Do you find companies that struggle with justifying putting the IIoT in? Because it's expensive compared, because there's always a cost balance. If it costs me $10 million to fully instrument my plant to save a $1 million event, then I'm losing money on it.
So I have two answers there. The first one is, sure, everybody's going to push back because they say it sounds expensive. You have a wreck in your car, it goes crunch, and you say, "Ooh, that sounded expensive." Well, a lot of times when I talk, people say, "Ooh, that sounds expensive." It's like wrecking your car. I hate that thought, though. I'm really not expensive. So it really may not be as expensive as I think, because we've been going through a digital transformation for many years. Transformation isn't an event. It's not an event that happened in 2004 or 5. It's an event that's been happening over time. It's a journey, right? We're all somewhere along that journey. So you're probably more digitized and probably transformed more than you already know. So this may sound like a pie in the sky. It's really not, and it isn't hard to get there. The part about the instrumentation, you have a data historian, almost every process does, because everybody wants to understand what's going on in the plant, what's happened in the plant, for a lot of different reasons. So if you have a data historian, you've already got sensor data. This isn't talking about specialized sensors that we're talking about the previous question here, or specialized on 40,000 psi hypercompressor. This is just data that you already captured. It's valuable, especially as it relates to IOWs, because IOWs, if you think about it, they're the same thing that operators use to measure for their process quality. They're always managing on and off spec products, because on spec, they make big money. Off spec, they make something. Too far off spec, it's wasted, and they have to recycle and spend the money again. So that they're already capturing that data. So as it relates to IOWs, that's a simple fix. You're capturing the data probably already. So it isn't going out there and tooling yourself. You're typically already tooled. Now the part of that journey, digital transformation journey, is where you're capturing even more valuable data, the kind of data that we talked about here, or maybe it's high corrosion rate area, and you want to install some permanently mounted or temporarily mounted UT sensors or eddy current array sensors, things like that. But again, those are on an as-needed basis. In most cases, the plant already has or captures most of the sensor data that you need. When you're talking about the IOWs, again, pressures and temperatures, you've got that right there in that buffet, that data historian. You have it at your DCS, PLC, SCADA, doesn't matter. You can integrate to data historian or the live data from DCS, PLC, SCADA, whichever the case.
I was also going to add to that, sometimes people do say that, oh, it's very expensive, things of that nature. And a lot of times I will tell them, I would look at your high risk assets or your bad actors. And maybe that's where you would want to start. And if they find a lot of value in that, then maybe they want to extend it.
That's a very good point. Scalability is the key. And in almost every case, not only do customers do that or end users do that, but we recommend that you focus on your critical assets, your high critical assets first. And really, this is kind of like cutting your teeth on that journey. The critical assets first, and then move on to the
I think this will
to
have
a
to
holistic.
be our last question.
Okay.
So one of the excuse me, one of the issues that you find, you talk about silos. You got organizational silos, information silos. Who captures? How do they understand it? And then one of the issues, like with sensors, is on the maintenance side and then on the operating side, is a lot of maintenance is driven by the operations and understanding what is being captured. The process itself. You talk about losing mass. We had a situation where we had titanium agitators, and we basically ran them until they fell apart because they didn't want to open up. However, the sensors in the process information, I'm from maintenance, and we started dwelling into that, and then starting to look at the PI information or the historian information, developing our own PI tags. They allowed us to do that based on our knowledge, and just kind of reaching into it and saying, hey, we can find out why when that agitator is losing mass, and understanding what the purpose of that agitator was quite often confusing as well. So putting all of that stuff together, it can be a bit confusing, but it can be very rewarding. But getting to that point sometimes is very difficult in an organization.
So you just saw the solution, because you just talked about operators and capturing data, and then sometimes driving the maintenance plan, because they're actually going to create notifications and work orders and all that good stuff. So I talked about that operators collecting real-time data from the field, being a human as a sensor, from gauges that aren't digitally connected, and from liquid level gauges, that sort of thing, whichever kind of gauges. We talked about things that they're visualizations, having these checklists, so to speak, so they can check things off and take pictures and videos, but then also generate a notification. So now you just, in this digital twin, you've actually looped in your maintenance, your engineering, your inspection, and now they can all see what that operator is seeing even before that failure happens. If you're capturing the data from the historian, then of course you see what the sensors are telling you too. It isn't hard to put all that together, and one can contextualize in that digital twin what's taking place to be a lot more proactive in your maintenance activities.
I think we're going to have to wrap it up. Thank
Sure.
you very much, Floyd. That was really good information. I enjoyed it. I got a lot out of
Thank
it.
you, thank you.
And
Angela's gonna be
I'm
talking this
curious-
afternoon in here, the same room, about 2:30. And she's gonna talk more about the data analytics and data capture, that sort of thing. So y'all come back and join us at 2:30.
Excellent. So thanks, everyone, and we'll just got to transition the room now. Thank you.
Thank you so much, Bill. I
great.
appreciate it. Let me get some water. Oh, I guess I'll